take you to the top. You will clear the highest hurdle, break the hardest rock. If you do a little work, you can have a lot of fun. You can do anything. If you show a little love, you can do anything. Show a little love.
Endeavor Houston, good morning to the blue team. We just thought we'd play you the Prop Fido theme song for the mission.
We thought you were playing a great country western dance song.
Copy. Welcome aboard Endeavor. I'm Kevin Kriegel, the commander. I'm getting ready to do a status check on the Maggard, or the Mini Airborne GPS Receiver. GPS stands for Global Positioning System. It's a network of satellites circling the Earth that gives users on the ground and in the air precise three-dimensional positioning. In order to get this positioning, you need to receive at least 4 satellites. We're testing this system on board the shuttle, hopefully using it in the future for landings as our normal navigation system, TACAN, eventually get phased out. As you can see on this display, we've got a map of the world and it's showing our orbital track. So we can determine exactly on orbit where we are using the Global Positioning Satellite system with the Maggard receiver. The Maggard on this particular SRTM mission is also the backup for the primary SRTM Blackjack GPS receivers. If it has any dropouts, then we'll use the shuttle data to go ahead and look at the data on the ground so that we can determine where the satellite was positioned. So I'm going to check the data for today to pass on to the ground, and it looks like at an MET of 15 hours, you gotta like these clocks. At an MET of 6 days, 2 hours, and 23 minutes, we are on C GPS 048.2, and the disk is 525.6273 megabytes. Well, thanks for this short trip aboard Endeavor on the middeck. Thanks.
Our radar system consists of a main antenna, which is located in the orbiter's cargo bay, as you can see here in this small model, and we have a secondary antenna deployed on a 200-foot or 60-meter long boom, and this secondary antenna sits out here. However, what is not very often known is that the relative position between the two antennas must be known with an extremely high accuracy. And for this, we have a system that we call AOTA, or with its nickname, Lumpy. And I would like to show you more about that. Let's take a look into the cargo bay. What we see here, most importantly, just disappearing in the upper right-hand corner, is our beautiful Earth. And the cargo bay is basically one big antenna. The AOTA system that I just referred to is the big hump that you see right in the middle, and it consists of several electronic devices that measure the distance and the attitude of the outboard antenna relative to the orbiter and the inboard antenna. Let's look along the same line of sight that AOTA is doing and look how long this mast really is. It will take a while for the camera to zoom out, and that tells you that 200 feet are really a long distance. An impressive sight on TV as well, as if you look out the CDR's window. And there at the very end, the outboard antenna will come into sight soon. And here it is. It is a little bit black on one side, but it will be more visible right here. And if you look right in the middle of the black area of the antenna, you saw 3 stalks, and they will come right back. And on these stalks, there are LEDs mounted, and these LEDs are observed by the target tracker that is inside our AOTA system. Another system that we have is a so-called electronic distance meter, and the combined data of those 2 devices, which are crucial for the success of this mission, gives us an accuracy of about 2 millimeters or 1/10 of an inch, which is quite amazing given the fact that the antenna out there is not entirely stable, but moves around slightly though, because the mast is very rigid, but still a little bit. Of course, we don't go outside to do the measurement. We use a computer that we have right here, and this computer actually is the crew interface, but not only the crew interface, the POC, the ground control team on the in Houston, uses this computer to command the AOTA system, to retrieve the data, to record the data, and to analyze them.
This is the right side of the shuttle cockpit. That's PHR number 3, which normally is recording X-radar data. Over on the left side of the shuttle cockpit, we have 2 more recorders, PHR number 2, which is normally a C radar machine, and PHR number 1, which is also normally a C machine, and those 2 ping-pong back and forth. Above them is the recorder interface computer, which controls the routing of the data amongst those 3 computers, and it does it through this panel that we call L15. That's the location in the orbiter. And you can see all the cables that run down from the RIC, and back behind there they connect to our recording switching unit and to the PHRRs, which is the payload high rate recorders. Down on the mid-deck, we have a 4th recorder that we call a warm spare, because it is ready to go if required. It takes about 1.5 minutes to spin it up. It's in this blue rack that we call the mid-deck accommodations rack behind this door. All we have to do is release 1 bolt and pull the door open. You see the cue card right there in the center. That's a tape recording cue card. We pull that door open, and the recorder is ready to run as our backup machine.
Okay, we were just finishing up our shift, and Gerhard and Kevin and Janet were taken on their shift when we had a problem with PHR number 1. It lost interface with C radar data, and so we had to do a fairly quick reconfiguration to make sure we could get all the data we wanted. Early in the flight, Kevin and I had enabled a lot of the panels that had screws and connections to be loosened so that we could do this in the event that something like this happened. And so that seemed to pay off really well last night. The procedure was written to last about 30 minutes, and Kevin had some cables reconfigured, probably in less than 2, because the panels had been accessed and we'd been trained so well by the folks on the ground. So we got the cables reconfigured, and we then enabled the radar data to be going down to the MAR recorder, and we had the radar interface computer directly controlling that, where before it had only been able to be done by a hand controller. So we very quickly got back into a nominal configuration where all 3 recorders were getting the data we wanted, and then during some quiet times over the night, the other red shift, Kevin and Janet and Gerhard, did some tests on recorder number 1. They reset it, turned the power off, turned it back on, and that seemed to fix the problem. So now we've returned to the configuration that we started with. That recorder in the mid-deck no longer is being used. It's still a standby, and now we're fully operational back in a normal config. But that all was made possible by some quick work by Kevin and his crew, and some good training on the ground. So now we're just taking data like we did before.
Steve, I'd just like to talk about the current status of tape and battery. Now I'm working on tape number 5, and we so far MET 5 days, 2 hours, 38 minutes, 47 minutes, fly over Mexico.
And also, actually, we flew over Japan in daylight time on red shift, so it took 6 days, 7 hours, 35 minutes, 45 minutes for 10 minutes, Japan. We wanted to take Southeast Asian countries, but unfortunately all crowded.
Today, what I thought we would do is tell you a little bit about our special mast that we've got. You saw a brief picture before we went into the dark of the mast. I think it might be nice to take that picture back out to the mast, and we'll talk a little bit about what we've got. This mast is, as most people by now know, almost 200 feet long. It's about 60 meters, and each one of those bays is about 30 inches in length, width, and in each axis. And at the tip of that mast, there's a tip plate and a milk stool adjustment mechanism that holds the outboard antenna. What I thought we'd talk about briefly is how that mast extends, and to do that, we've got this great little model here that Momoru's holding on to, and if you can picture in your mind that this collapsed mast is inside a circular canister, then imagine if you're familiar with what's on the inside of a rifle barrel. There's actually rifling lines that enable a bullet traveling down the barrel to spin up. Well, the same sort of thing is on the inside of our canister. There's some rifling type grooves or tracks that the mast tips extend through, and that way it expands as it rotates as it expands. And as Janice grabs hold of the outer bay here, you can see that the tips rotate through the rifling screws in the canister, and then they lock into place once they become fully extended. The battens that we see here that are black on our mast are made out of graphite epoxy, and the cross members are made out of titanium. The end joints are all made out of stainless steel. And then as each section locks into place, the center screw drive that's driving this thing rotates into a different direction. So as each section locks into place, it rotates and counter-rotates as each bay locks. It's really an ingenious mechanism.
I wonder during the last couple of days how much of a horse race you thought it was to find the propellant to finish the mapping mission you started out on. Were you confident? Did you have reservations or serious doubts?
Well, I have first-hand experience with the expertise of the prop team on the ground, and I had no doubt that those folks were going to find a prop to get a full mission, and sure enough, they did.
Given the mysterious white object that shot out of the cargo bay a couple of days ago and the problem with the nitrogen gas line, does that make you a little more nervous about bringing the radar mast back in? It just seems that it would be easier to send it out than to fold it back up into a small can.
Absolutely not. I was involved in some of the early testing as an observer, and I know how superb the team out AC Able that built the mast and the JPL folks that work on the structure, how hard they worked, all the things they looked at to make sure this mast would work for us, how they continued through all the testing to work every problem as hard as they could and get this mast in perfect shape. And I think that was demonstrated in the deploy of the mast, which went absolutely flawlessly. And I have full confidence that they'll be able to get that back in as planned.
I have another question to Mr. Thiele, a very personal question. You are the father of 4 children. You cannot bring any gifts, no material gifts from this mission, but maybe you can bring them back something else and to other young people. Message, an insight? Yes, and I'm trying that already. in the Space Forum for German space travel. We often ask, what do you have to do to become an astronaut? And often you hear one has to be a good scientist. And my answer is, maintain your dreams. Your dreams are your future. Dreams are what propels us further and what has brought us for the last centuries or millennia. It takes sometimes long, but dreams become reality, and that would be my message to the children, but also to the adults. Many thanks for this message, Mr. Thiele.
Good luck for re-entry and for the landing next week.